When people first hear the phrase data repository, they often picture a single database sitting quietly behind an application. But in real environments, a repository is any place data is collected, stored, searched, and reused. That can be a database, a data warehouse, a document store, an object bucket, a search index, or even a shared analytics environment where many teams read and write. What makes repositories special is that they attract value over time, because once data is centralized, it becomes more useful, and that usefulness often drives wider access, more integrations, and more copying. The result is that repositories become high-impact targets for attackers and also high-risk sources of accidental exposure when permissions drift or data gets reused in ways nobody originally intended. The goal here is to learn how to secure repositories using 4 ideas that work together rather than in isolation: access control, encryption, redaction, and masking. By the end, you should be able to explain not just what each control does, but where it fits in a defensible architecture, especially in cloud environments where repositories are easy to create, easy to share, and easy to misconfigure. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A strong design begins with access control, because if you cannot reliably limit who can reach a repository and what they can do, everything else becomes harder and more fragile. Access control means deciding which identities can read data, which identities can change data, and which identities can administer the repository itself, and those are very different risk levels. Beginners often assume access control is just a login screen, yet repositories are usually accessed by applications, services, analysts, automated jobs, and administrators, not only by end users. In cloud environments, this gets more complex because identities may come from different places, such as an organization directory, a service identity system, or temporary tokens used by workloads. Good architecture treats each access path as intentional, meaning you know why it exists and you can explain how it is authorized. The first big misconception to avoid is thinking that once an identity is inside a private network, it should be trusted, because modern breaches often begin inside, and cloud networking can make internal boundaries far more porous than people expect. A secure repository begins with explicit access decisions that are tied to identity and role, not to vague assumptions about being internal. Once you accept that access control is foundational, the next step is to structure it so it stays understandable as the repository grows and more people want access. The simplest approach that scales is to start with least privilege, meaning each user or service gets only the minimum access needed for its task, and then you add access deliberately rather than granting broad access up front. This is where the difference between read access and administrative access matters, because administrators can often bypass normal restrictions by changing permissions, exporting data, or creating new access paths. In cloud settings, administrative roles are particularly sensitive because management interfaces can allow snapshot creation, replication, and sharing, which can move data to new places quickly. A common beginner misunderstanding is assuming that repository administrators are always trustworthy and therefore do not need strong controls. But administrators are high-value targets for credential theft and social engineering. Another misunderstanding is assuming that service accounts are harmless because they are not people, when in reality service identities can have broad access and can be exploited if applications are compromised. A durable design therefore separates duties, restricts administrative functions, and uses carefully scoped service permissions that align with the exact data operations the service must perform. When access models stay clear, it becomes harder for permission sprawl to quietly turn a repository into an open vault. Access control also needs to be applied in layers, because repository security is often defeated when one layer is strong but another layer is accidentally permissive. Network-level controls can limit which systems can even reach the repository, which reduces attack surface, but network controls alone cannot express who is authorized within that reachable set. Identity-based controls can decide who is allowed, but if the repository is reachable from everywhere, attackers gain more chances to attempt abuse and more opportunities to exploit mistakes. Inside the repository, you may also need object-level controls, such as table-level permissions, row-level constraints, or collection-level policies that limit what data is returned. In cloud repositories, a single bucket or data set might hold both public and sensitive data, and object-level controls help prevent accidental mixing from becoming accidental exposure. Beginners sometimes assume that placing a repository behind a firewall makes it safe, but if credentials are stolen, the firewall becomes irrelevant, and if the application itself is compromised, the application becomes a trusted proxy. This is why architects emphasize defense in depth, where network placement, identity enforcement, and repository-level authorization reinforce each other. The repository should be secure even when one layer is stressed, because real incidents rarely respect neat assumptions. Encryption is the next core control, and it is best understood as a way to reduce the harm of certain kinds of access rather than as a universal shield. Encryption at rest protects data when storage is copied, stolen, or accessed outside the normal permission system, such as when someone gets raw access to disks, backups, or snapshots. Encryption in transit protects data while it moves between clients and the repository, which is especially important in cloud environments where network paths may cross shared infrastructure. However, encryption does not eliminate the need for access control because authorized clients must decrypt data to use it, and attackers who compromise an authorized identity can still read the data through normal channels. A common misconception is thinking that encrypted data is safe no matter who can access it, but if many identities can query the repository and receive decrypted results, encryption at rest does not prevent leakage through legitimate reads. Another misconception is assuming encryption is purely a technical toggle, when the real architectural challenge is key management, meaning who controls the keys, how keys are protected, and what happens when keys need to be rotated or revoked. In cloud environments, key services can centralize this responsibility, but that centralization also makes key access a high-value target that must be monitored and restricted. Encryption helps most when it is paired with strong identity controls and a realistic key lifecycle plan. Key management is where encryption either becomes a durable layer or a fragile promise, so architects pay close attention to the separation between data and keys. If the same system that stores data also stores the keys with weak separation, then compromise of that system can unlock everything. If keys are controlled by an independent security boundary, with strict policies governing who can use them and under what conditions, then encryption can meaningfully reduce the impact of certain compromises. Cloud architectures often rely on centralized key services and policies that grant limited key usage to specific workloads, which is powerful when done carefully. Yet beginners should know that key access is itself an operation that can be abused, so monitoring key usage is not optional if you care about detecting unusual behavior. Another part of durability is rotation, because keys should not remain unchanged forever, and designs that cannot rotate keys without downtime or data loss are designs that will eventually fail under real-world pressure. Recovery planning matters too, because if keys are lost or locked away without a way to restore legitimate access, availability collapses in a different way. A secure repository design treats keys as critical assets, with controlled access, logging, and governance that match the sensitivity of the data they protect. When key management is explicit, encryption becomes an enforceable boundary rather than a comforting word. Redaction is often confused with encryption, but it solves a different problem, and it becomes especially important when the right people need access to some data, but not all of it. Redaction means removing or obscuring sensitive parts of data so that the remaining data can be used safely, such as removing personal identifiers while retaining transaction details for analysis. This is different from encryption because encryption protects data from being read at all by unauthorized parties, while redaction allows data to be read in a reduced form by authorized parties who do not need the sensitive details. In cloud environments, redaction is valuable because data is frequently reused for analytics, reporting, troubleshooting, and support, and those uses often involve broader audiences than the original transactional system. A beginner misunderstanding is assuming that if someone is authorized to access a repository, they are automatically authorized to see every field in every record, but privacy and least privilege usually demand more nuance. Redaction supports that nuance by letting the repository serve different views of data depending on role, purpose, or context. Another misunderstanding is assuming redaction is only a display feature, when in fact it can be applied in stored datasets, derived datasets, logs, and exports to prevent sensitive data from escaping into places where it does not belong. When redaction is designed thoughtfully, it reduces exposure while preserving the utility of the repository. Masking is closely related to redaction, but it is important to treat it as its own concept because it is often used for different reasons and can create different risks. Masking typically means replacing sensitive values with altered values that preserve format or general characteristics, such as replacing a real account number with a realistic-looking substitute. This is commonly used when teams need data that behaves like real data for testing, development, analytics, or demonstrations, but they do not need the actual sensitive values. In cloud environments, this matters because development and analytics platforms are easy to scale and share, and the temptation to copy production data into non-production spaces is strong. Masking reduces the chance that non-production environments become secret treasure troves of real customer data. A major beginner misconception is thinking masking is the same as encryption and therefore reversible. But good masking for non-production use is often designed to be non-reversible, so that even if masked datasets are leaked, the original sensitive values cannot be reconstructed easily. Another misconception is thinking that partial masking is always safe, when in reality, leaving too much structure can allow re-identification through correlation with other data sources. A secure masking strategy therefore considers what an attacker could infer, not just what is visibly hidden. To make redaction and masking effective, architects also need a clear understanding of data classification and data purpose, because you cannot safely hide what you have not identified. Data classification is the practice of recognizing which data elements are sensitive and why, such as personal identifiers, authentication secrets, financial records, health details, and proprietary business information. In cloud repositories, classification can be challenging because data comes from many sources, schema changes happen frequently, and new fields appear as teams add features. Beginners sometimes assume sensitive data is obvious, but sensitivity often hides in combinations, such as a seemingly harmless identifier that becomes identifying when paired with timestamps, locations, or behavioral patterns. A strong design uses classification to drive policy, meaning it is not just a label, but a rule-making input that determines who can access which fields must be encrypted, and which fields must be redacted or masked in downstream uses. Classification also supports auditing, because you can verify that sensitive fields are not appearing in places they should not, such as logs, exports, or analytics datasets. When classification is tied to real repository controls, it becomes part of the architecture, not a separate compliance exercise. That alignment is what keeps repositories from becoming accidental privacy failures as they grow. Another architectural concern is how repositories are used by applications and services, because the easiest way to defeat careful repository controls is to build an application that retrieves sensitive data and then redistributes it widely. Even if the repository enforces tight permissions, an application that acts as a trusted middle layer can become an unintended data exfiltration channel if it is compromised or poorly designed. This is why security architects think about end-to-end data flow, not just repository boundaries. An application should request only the data it needs, store only what it must store, and return only what the user is authorized to see, which ties back to access control and the principle of minimizing data exposure. In cloud environments, service-to-service calls can multiply quickly, and a single repository might feed many downstream systems, each with its own identity and risk. A beginner misunderstanding is thinking that if repository access is restricted to a single service, the data is safe. But if that service is broadly reachable or has weak authorization checks, it becomes a high-value target. This is where redaction and masking can reduce damage, because even if a service retrieves data for a legitimate purpose, it can retrieve only redacted views for users or masked versions for non-production workflows. When repository controls and application design work together, the system becomes more resilient to compromise of any single layer. Cloud architectures also introduce the problem of replication and caching, which can quietly spread repository data into more places than the original design intended. Data might be replicated for performance, availability, analytics, disaster recovery, or search, and each replica becomes another repository that needs controls. Caches can hold sensitive data in memory or on disk to speed up requests, and those caches may have different access controls and monitoring than the primary repository. Snapshots and backups can create point-in-time copies that are easy to share or restore, and in cloud environments they may be created automatically, which means they can also be exposed automatically if policies are weak. Beginners often assume the repository is one thing, but in practice it is an ecosystem of copies, derived datasets, and supporting storage. A durable design therefore treats replication paths as part of the security boundary, ensuring that encryption, access control, and data minimization apply to replicas as well as to the source. It also considers how redaction and masking apply to derived datasets, because analytics copies should often be less sensitive than the source. Monitoring and inventory become essential here, because you cannot protect what you do not know exists. When you design repositories in the cloud, you are really designing the control of data movement as much as the storage itself. Monitoring and auditability are also core to repository security because many repository risks involve legitimate credentials being used in illegitimate ways, which is hard to catch without visibility. Good monitoring includes tracking who accessed what data, when they accessed it, and what kinds of actions they performed, such as bulk exports, unusual query patterns, or unexpected administrative changes. In cloud environments, monitoring also needs to cover management actions like sharing, replication changes, key policy changes, and permission modifications, because these actions can reshape the repository's security posture quickly. A common beginner misconception is thinking logs are only useful after an incident, but well-designed monitoring is also preventive because it can reveal misconfigurations and suspicious patterns early. Another misconception is assuming that if access control is strong, monitoring is unnecessary, but access control can be bypassed by stolen credentials, insider misuse, or configuration drift. Monitoring supports accountability, which discourages casual misuse, and it supports rapid investigation when something goes wrong. It also supports validation, because you can confirm that redaction and masking are actually preventing sensitive fields from appearing in logs and exports. When visibility is designed intentionally, repository security becomes an ongoing capability rather than a one-time setup. Governance keeps these controls from decaying over time, because repositories tend to grow, teams change, and urgent business needs create pressure for shortcuts. Without governance, permissions expand, key policies get loosened, redaction rules get bypassed, and mass datasets get mixed with real data until nobody can confidently describe what is protected. Good governance does not mean bureaucracy for its own sake. It means clear ownership, clear approval paths, and periodic review of who has access and why. In cloud environments, where self-service creation is common, governance also includes guardrails that prevent risky defaults, such as preventing public exposure, requiring encryption, and limiting who can create new sharing relationships. A beginner misunderstanding is thinking governance is separate from architecture, but in security, architecture governance is how design intent survives contact with reality. If you cannot maintain the control set, it will drift, and drift is a common cause of data incidents. Governance also includes incident readiness, meaning you know how to revoke access, rotate keys, and investigate suspicious queries without shutting down the entire business. When governance is built into the repository's operating model, access control, encryption, redaction, and masking stay aligned and effective. As we wrap up, the most important lesson is that securing data repositories is not a single control choice, but a coordinated design that manages who can access data, how data is protected when stored and moved, and how sensitive elements are minimized in the places where they are not needed. Access control establishes the primary boundary and must be identity-driven, least privilege, and resilient against drift, especially in cloud environments where sharing and automation can expand reach quickly. Encryption reduces the impact of storage exposure and network interception, but only when key management is treated as a first-class security problem with clear separation, monitoring, and lifecycle planning. Redaction reduces exposure by removing sensitive elements from views and outputs when users and systems do not need them, preserving utility while limiting privacy risk. Masking supports safer reuse of data in non-production and analytic contexts by replacing sensitive values so that workflows can proceed without dragging real secrets into weaker environments. When these controls are designed together, they reinforce one another, and the repository becomes something you can explain, monitor, and maintain rather than something you simply hope stays safe. That coordinated approach is what turns a repository from a growing liability into a defensible asset that supports both security and responsible data use.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.